Hello everyone, welcome to our recorded class uh, for the Crashworthiness session. So in this session we'll be first discuss the projects that everyone needs to complete for completion of this course. So as per as we had decided earlier, we are going to look at few crash cases. Majorly we'll be looking at frontal crash, then side crash, and then roof crash. So with the given license limits which we have on student edition of HyperWorks, we have 100k element limit on radios as well, and with that uh, I have reduced a full vehicle model to subsystem models. And so mainly for frontal crash, all the important parts from that car have been included. So now in this case, the things we will be looking at in frontal crash are mainly a full frontal crash with all the sectional forces and some of the intrusions. So to start with, first of all, I am giving you a reference model. So in the samples, you have neon 300k elements and Taurus A00 or even neon 1 million elements. So you can open neon 300k elements and this will be your reference file. This model is the full scale model with 300k elements, and well, it is huge in size for our student edition to solve. Now for the projects, you have 3 projects given. First of all, we have neon front. Now let's open that, and what we have, well, so what I would suggest you is you open the same model in both HyperCrash and HyperMesh. So currently HyperMesh has the limitation of 100k nodes, whereas for HyperCrash it has only 10k node limit. So this file which you are able to open, it has 99,000 nodes. If you try to export this in HyperCrash, you won't be able to export, and that is why you will have to operate this full model in HyperMesh. Now in HyperMesh, there are few easier things to do and few easier things to take care of. Most importantly, whatever you create, always use the solver browser. So you can go to view browsers, HyperMesh, and solver browser. If you click on this, you will get this browser over here, and in that you will see all the list of keywords. So if you want to create, let's say, a rigid wall, you can simply right click here and go for R wall. That is the control card or block card for the rigid wall. Then in that you can select cylindrical or plane or whichever you want. So that way you'll have to operate through this and you will get through this easily. Apart from that, for model checker, what I would suggest is you write out whatever you want in this. Then you can take this file, come to HyperCrash, and then you can run the model checker. Now all the issues that you see in the model checker, you can clear those issues in your HyperMesh window, and that way you can move forward. Just as a sanity check, before submitting a run, I always advise do a model checker run, and that can be done in HyperCrash, and the corrections will be done in HyperMesh. Apart from that, in tools, in model checker, radius block, this also is a model checker available in HyperMesh. It's just that it is little tricky to use that as of now. So what I will suggest is, if you click this button, you will get the model checker running here. Now it can take time to run, but in the end, the task we need to accomplish at hand is over here. So first of all, to start the model, you need to check the unit system, either follow megagram, that is tons, mm and second, or kilo, mm and millisecond, based on how we have discussed in our classes until now. I would recommend this particular unit setting, but in the output or in the project report, you have to give me results along with their units. So whichever unit system you follow, I'm okay with it. It's just that you have to mention your own units when you give me the results. Then in this one, you might have some interfaces defined already, but in your case, you have to define a global interface. You may get rid of all the interfaces that are not required. I'm going to ask you for your model as well. If I see that there are additional interfaces that are those are not really required, that will cause deduction in points. So you have to make sure that only the required interfaces are there. If there are extra interfaces, they can cause a run to run slower, or a simulation to run slower, and that is exactly what we don't want here. Then penetrations check, you can do that check in HyperMesh as well as HyperCrash. In HyperMesh, what you can do simply is, now here you have so model checker has thrown out some issues over here. You can take a look at those. And then you can apply corrections. I would highly recommend using the HyperCrash model checker though. Well, anyway, so for penetration checks in tools, you have a penetration checker, and that can do the trick for you. As of now, I think there are not many penetrations in this model. If there are very few minor penetrations, I can also recommend you to do the changes manually than going by penetration. So in that case, you can simply select these nodes, press Shift F4, select the nodes, and then move whichever direction you want. Now this is just an example, doesn't mean there is a penetration over here. The mesh for this model is really coarse, but because we have such a coarse mesh, we could at least include the major part of the BIW, which is very crucial in Crash. So in these three projects, what you will realize is that the BIW is the main guy which is taking care of all the crash loads and which is saving you in a car crash. Now coming back to our presentation, you have to create and correct any rigid bodies that you need to do. So if you see any flying part around, what I'll suggest you is you can take this model to HyperCrash, and then maybe you can isolate one of the components. Let's say I'm isolating this one, and I'll close the model checker for now, and then I can click this button, display parts connected to the selected part, and I see there are so many components still connected. So I'll just review how they are connected to each other. If the connection is not sufficient, you can use your judgment here. Now this component is looking like a rail, and it has a flange on the end. So it must have been welded together with rest of the components. So if I don't see the spring elements or weld elements over here, then there is some missing connection. Now as of now, in this case, I see that the spring elements are properly aligned. So these may be connected very well, but you will have to do this check yourself. Apart from that, in quality, what you can do is first select the whole assembly as such, and then in quality, there is an option for checking the connectivity of tree selection. So you have selected the whole assembly in your tree, and then if you check this, you might get some idea. Now here I see that there are few springs or few parts which are not connected anywhere. Perhaps you want to take a look whether they are connected properly, or if they are not connected, do they still really are needed to be connected? Are they needed in our analysis at all? For me, in general case, if this is a joint, I will look what parts it might be looking to join again. Now if those parts are not existing in the model, then there is no point in keeping that joint. So for that purpose, you always have your Neon 300K model, and you can always trace back this joint, you can trace back this component there, and you can see where it is exactly connecting. If those parts are not in the model anymore, then you don't need that joint as well. Alright, so apart from that, let's get back to the presentation. So you have to compare the model. You have to create a rigid wall with friction 0.1. You can review the full scale model 300 with 300k nodes to see how the rigid wall was created and what all nodes were selected in that for the rigid wall contact. Then you will have to compare the model weight. Now this is the tricky situation. In HyperMesh, in Solver browser, you can see all the add masses listed over here. Now you can choose to delete these. You can always list them down over here in model balancing, and you'll see the whole list with along with the numbers, exact numbers. Apart from that, you can always go from browser, added mass. You can double click on this and you'll see what was the added mass on that particular node. So at this particular node, the added mass has been 1 gram. Now I'm not sure if I really care about that mass with 1 gram. So in that case, I can maybe delete those masses and then I can look at the system as a whole and I can decide where I want to add the masses. Ultimately, what you need to do is you'll have to open the 300k model, that is higher resolution model with all the parts included, and you have to do the balancing. You'll have to see where the CG is coming up. You have to match the CG with that particular number. So currently your CG, if I really go on to plot this, show CG point, it is coming up over here. But as I mentioned in our very first session, usually the CG of the car is right in the line of the driver, that is somewhere here. So if you want to bring that CG somewhere here, you want to add some more mass over here, and then perhaps for the component level analysis you want the 700 kg weight. So in that case you want to make sure that your whole assembly weight is also 700 kg. Right now it is just 188 kg, so you have a lot of scope to do that. So mainly for weight addition, what I'll suggest is make use of the floor component, because that doesn't hurt your Z component of the CG. I don't care where your CG lies in with respect to Z, but with respect to X and Y, it has to lie closer to what the full scale model is showing you. Now location of CG will matter a lot, because the car as a whole, when it impacts with the rigid wall, the location of the CG will decide whether the car is going to roll forward, like yaw, or there won't be any such effect. So those things are important. So try matching the masses, or try matching the CG, and in that process you might end up changing some of the masses on this particular list. Well, what I see as of now, the number of masses over here, now this is like 871 gram. This could be significant, but if you see very small numbers such as these, you may get rid of those, and that will not make huge difference to your simulation. Anyway, let me know how you find this 700 kg target helpful. If you're not very comfortable with it, we can revise this target, but I want your feedback whether you are able to do it. If you are able to do it, report to me and we'll continue with this. Otherwise I'll have to revise this particular component of this project. Otherwise everything else is pretty rigid. You have to apply initial velocity of 35 mph, and then time step of the simulation should be between 0.5 microsecond to at the minimum 0.1 microsecond. I would suggest or recommend to try for 0.5 microsecond and do whatever changes are needed in the model. Your mass error globally should be less than 5%, so make sure of that. Output request. Now output request will be mainly the sectional forces in rail components. So now look carefully where exactly we want all these cross-sectional forces. First of all, I'll be looking for a cross section in this particular region. Well, so I'll be looking for a cross section in this particular region. You can look for this node number and create a section right in this line. Apart from that, we want a section in shotgun. Once we receive that node ID, we can put that here. Apart from that, I also want to see the actual forces that are received on the rails from the bumper. So now you'll see here, bumper is connected to the rails through some weld elements, which are represented as spring. Now I want to see how much force is being received on the rails from the bumper. So you may define a contact between these two, and you can request for contact forces. As long as in the result I'm getting the correct force value, I'm okay with it. I don't care whichever way you get those. Then shotgun cross-sectional forces, you want to take a shotgun cross-section around this region and want to tell me how the forces are being received there. Apart from that, A pillar cross-section. So well, there is a hinge pillar over here. Right from there you start the A pillar. In this region I want to see what are the cross-sectional forces. Then apart from that, now we can use this model meanwhile. Yes, in fact numbering will be pretty easy here. So I'll switch this off. Alright, now for shotgun cross section, we want forces in this particular cross section. I want forces received on this particular surface. Then I want A pillar cross sectional forces, so perhaps this point. Then apart from that, the hinge pillar cross sectional forces. So in this case they may not be very crucial, but they are a part of exercise in one of the crash tests. So we have around 1 2 3 4 and 5 points. Similarly on the right side you will do the same thing, so there will be 10 complete cross sections. Apart from that, so you wanted to see the numbers 174247. What I'll urge is remember this picture from the video and try to replicate the same thing in your model. Well, you know this node ID already, and now these are very visible from this end. 174344, 139604. Around this region is enough, so you don't have to exactly go for the exact node. Same thing on the other side. So apart from this, the next output challenge will be acceleration curve received on the accelerometer at base of the B pillar. Now here we have the B pillar. There is a component called rocker in B pillar. So this rocker component, what it looks like, can you switch off please? No? Okay, anyways, I can perhaps indicate it much faster over here. So this rocker component it's exactly the one which I just isolated. So these rocker components, an accelerometer will be mounted on this. So you can mount an accelerometer over here. You can create an accelerometer at the base of B pillar on the rocker, and in this accelerometer you will have to request the output so that I can get the accelerations in X direction, Y direction and Z direction, and in the end you have to plot the acceleration curve. So apart from that, intrusions on the dash wall. So for the intrusions, let me take you to HyperCrash. So on the dash wall, usually the major intersections are located at the foot pedal. So you want to look at a particular node, let's say this particular node. Then you also want to look at the brake pedal intrusion. So we'll look at this particular node. We'll switch these on. So there is 66695 and 66244. Alright, so you should be requesting these two intrusions as well, and these intrusions should be requested with respect to a frame of reference. Now that frame of reference can be based on some frame over here, and with respect to that you'll have to request this, because in global these two nodes are moving in X and they might have some yaw, they might move in Y as well, in Z as well, and that can be very chaotic. Whereas if you request it with a local frame of reference, the relative motion until the impact will be 0, and once the impact happens and once there is an intrusion, you will get some reading on that particular curve. So that is one way of doing it. Or what I can do is perhaps I can create a very less stiffness, a spring with very less stiffness. So a spring between 66695 and 121739. So I can create a spring over here in between these, and with that spring I can check the reduction in length of the spring with respect to X, or in the global X, and that can give me my answer. So there is another way of doing that. So you can choose whichever you want, but in the report you'll have to mention which way you have used to get this output. Both ways have been accepted industrially. It's just up to engineer to engineer which way they want to use. So you'll create a spring between these two nodes. The only trick here is that the stiffness of the spring should be very small. So 0.001 kilonewton per mm. That is still 1 Newton per mm, and that is still a good stiffness. So maybe 1 to the power e minus 4, e minus 5, that can be somewhat acceptable stiffness. It should not make any difference to the physicality of the problem, and that is why the stiffness should be very low. Alright, so that completes your frontal crash assignment. So for the submission, the files that you will have to submit is your 000.rad, 1.rad, then in the result files 0.out, 1.out. So that should tell me what energy error and mass error have happened in your model. Then I want your T01 file. Along with that I want your H3D file, and finally a presentation, or maybe 2 or 3 slides where you want to put all the results together and you want to give me a systematic view how you went about this task. Now all the questions that I have asked, which method you are using and all those things, you have to mention that in the presentation or those slides, and in that you have to mention what errors you have received, and well, ultimately all these results as well. So sectional forces, I only care about the peak of that force. So You can include the whole picture of that sectional force as well as the peak. You have to measure it yourself and put that value just besides that graph. For intrusions, what you can do is, well, you can simply tell me the number or show me the graph as well. So same thing for intrusions. Acceleration, you'll have to only show me the graph and also tell me the maximum value. So pretty much same approach for all of them. For accelerometer or accelerations, be careful about how you define the accelerometer. If you go back to our session, that can perhaps help you very well. The last session where I explained how to create an accelerometer. Okay, so then we'll move to our next topic, side crash. For side crash, why don't I have a picture here? So this is frontal. Import new section. Alright, for side crash, you can compare, or the reference you can use from this particular model, side reference. For frontal, you can use this as a reference. So the car had the front side on this side, the rear side here. Now I have isolated the BIW and door components in a way that this is going to be a pole impact test. So for pole impact, I have already aligned the pole in the other model, the 300K model, for reference. You have to replicate that same pole on this in this particular model. Apart from that, the initial velocities, which is the part of boundary conditions, you'll have to use it from the same model. So this kind of component analysis happens very popularly at a supplier location, because obviously they don't have the full car to test, but they have few components to deliver to their clients, which is the OEM. So while delivering all these components, they want to tell them how the crash behavior of these members is going to be during the crash, and that is what OEMs are always worried about. So supplier has to do all this, and that is why this is still a valid case. It's just that you have to be very smart while using your capacity of the license. So very similar instructions over here, just that in this case the sectional forces for the output, the sectional forces in the cross members will be interesting to see. So you can tell me the sectional forces that are coming up at the middle of these sections, or not at the middle, but maybe on the flatter section or the flatter side of this section. So maybe in this region and this region. Tell me the sectional forces by creating a section there and, well, aligning it properly. Apart from that, the major thing for side crash is the intrusion. Sorry about the resolution. Alright, so the major thing is intrusions and the peak velocity. So intrusion is very important because now your driver is located in this region. If during the crash, if this region intrudes too much into the car or into the driver compartment, there is a very good chance that driver will get hurt. So idea is to limit these intrusions as much as possible. So you'll have to measure the intrusions of the points in this region. So in this case, I won't be telling you which point, but in general, you'll have to take one point around this cross member and you'll have to tell me what is the intrusion. So in this case, just like how we did the intrusion study in the frontal, or how we are going to do in that case. You'll have to do similar smart trick here. So you may have to create a frame of reference, and in the data history, so when I say th of nodes, I'll say variable as def, that will give me displacement, but for nodes I can select some node very well, and right below that I'll have a chance to take the skew as well. So skew can be created on this side, which is much stationary, which won't have any deformations as such, and there you can create your skew and use that here. So with respect to that local frame of reference, all your intrusions will be measured. Or similarly, how we did for the other case, you can create a spring and you can simply measure the deformations in the spring. So in this case, the points of measurements will be mainly the driver compartment intrusions. So this point, then the area of the fuel tank. So the fuel tank usually comes after this link, so I want the intrusions on this particular node, and well, not really on this node, but so you'll have to take a node on the rocker. So you can very well choose the node sitting right behind this corner. You can take a node on the rocker, which is much more stable compared to this one, the component which is already formed, or which already has a contour. So the pure behavior can be received on the rocker. So please take the rocker for this, and then you can measure with respect to this point or some frame of reference at this location. So do it very wisely. If in whichever way you define the frame of reference, you have to be very careful with respect to that frame of reference, or whether it has X, Y or Z locally, and that kind of intrusions you have to measure, and you need to tell me. Then the third intrusions will be at the end of B pillar, so some node over in this region. So there are 3 nodes, one here, and one right at the corner. So with these 3 nodes, we have already discussed sectional force, then the peak velocity of the inner node of the door. Now if you have your driver with the seat aligned around this region, you want to tell me what will be the node, what will be the peak velocity for this particular node during the simulation. So obviously your car, there is going to be a pole impactor, or rather the pole rigid wall here, that is cylindrical rigid wall. Your car is going to impact into the rigid wall, and there are going to be deformation on this side. Now this deformation, if it reaches the inner side, I want to see at what velocity the node over here is moving. So let me indicate that node clearly in HyperMesh. So I can say that perhaps this node 33773, that will be important here. Alright, so you want to tell me the velocity at this particular node. So maybe th of node can help you with that, and in this case you will definitely need a frame of reference, so maybe a skew will help. So even in this case I want the very similar files. Okay, next we have roof crush. So for roof crush, again I have to reduce the example to fewer components. I won't be showing that on the screen, but let me quickly go through, because there is a huge list of instructions for roof crush. As we have mentioned, we have discussed earlier, roof crush is not really an explicit analysis case, but it is more of a quasi-static analysis. So the procedure or the masses will be different. Well, in this case, again your BIW is going to be the main thing that will take all the nodes or all the loads. But after getting the car in, first thing you have to do is get the impactor as well. So you'll import the car, you'll import the impactor. Then on the impactor you'll have to do few operations, and for that I'll insert an image over here as to which point is which on the impactor. So I'll share this presentation and it will have these points located on the impactor. Then you'll have to create the interface and apply the proper appropriate minimum gap and go for the best practices of the interface. Then in this case you'll have to define a gravity, but while defining the gravity, well, so looks like I need to open that. So roof crash, replace. So roof crush is another minimized model. It's just that on this side I have created a rigid body to take care of all the missing supports on this side, and this rigid body will take care of all the deformations that are happening on this side as a whole. So one part of this assignment will be to apply a 0 degree of freedom to this particular node, so that will restrain all these nodes from moving, and that will take care of all the load case that needs to be done. So you'll define an interface between the impactor and the roof. From there you'll go for gravity. So while applying gravity, make sure that the points you'll have to create a rigid body on the circumference over here and on the circumference of the shock tower as well. Now in a car case, the shock towers are supported by the shock absorbers, which are indeed supported by the wheels, and that gives you the support in the car. But now since we don't have the wheels or the shock absorbers, we have to assume that the displacement of these nodes, at least in Z, is 0. So you'll have to create a rigid body over here. The master of the rigid body should be given a boundary condition that it doesn't move in Z direction at all, the global Z at all. So there are 3 shock towers as such. There is first, second and third, and all of them have to have this similar boundary condition. Then there are impactor boundary conditions. You go on following these steps and you will get there. Then you'll have to impose a displacement on the impactor, and that will define your all the boundary conditions. Then there are few standard control cards that are needed to be defined, and then the engine file. So this creation of engine file you can use for even frontal and side crash. It's just that the solution time here for frontal will be 80 millisecond, Same is the case for side crash. So once you run for 80 milliseconds, you should be having enough results in your hand to do this. Alright, so with that, we have discussed the projects. Now we have 20 minutes left, and I'll quickly discuss some of the checks that you may have to go through while doing your simulations. So until now we have checked how to check the starter output for diagnostics. So in the starter you will have your mass or inertia listed. So this mass should be the mass in your starter output file should be matching with the intended mass, and in our case it could be 700 kgs or a revised value. Then starter file is also going to tell you about the minimum time steps. Now in your case, well, you are free to do the minimum time step analysis, but you will have to use some kind of time step control to take care of this. Then we have discussed this earlier, the incompatible kinematic conditions. You can choose to ignore those, or you can find a solution as the way we discussed during our session. Apart from that, we have already discussed that mass error, energy error should be 0. That is ideal value, but if it is not 0, then there are always some bounds within which your mass error and energy error should be lying. So to explain further about energy error, if the error is negative, we know that some energy has been dissipated, because ultimately the energy error is getting calculated with this formula, and this EK, EKR and EI are the instantaneous energies, internal and kinetic and rotational kinetic energies, whereas these energies in the denominator are all the initial conditions. So whatever is current upon initial minus 1, that gives us the percentage. Now if you have energy error negative, then you have dissipated some energy. That's why the total over here and here are not matching. This is lower than this. That's why the fraction gets smaller than 1. That is why you will end up with a negative answer. But there are always ways to negate the energy error. So there are few counterbalance measures that are listed over here, and you can always refer to these. For mass scaling, you know that there are huge deformations happening. The deformation of an element might be going out of control, and that is causing all this issue. So to do that, you should always animate the mass scaling, and you should see if there is any unnecessary mass scaling happening in a non in a region where it is not really required too much for analysis. So for quasi-static loading, you will see the similar condition in the roof impact, that kinetic energy upon total energy is less than 1%, and that is really an ideal condition. You should look for energy balance in your simulations. And this slide over here is explaining what is this external work. So if there is an external work, you'll see that the energy or the energy error is much less, or rather positive, not negative, because the energy is constantly getting added because of the external work. Now contact energy, in many of the complex simulations such as these, contact energy happens to be one of the important parameters that needs to be looked at, because suddenly you'll see that in the engine file the energy error is shooting from 1% to 99.9%, and that has many reasons or many implications, but one of them can be contact energy. Now contact energy can be mainly taken as penetration value into contact force. Then you need to make sure that the contact stiffness is set right, so you can follow the recommended practices, and then you can go about defining or getting a control of your contact energies. Same thing for hourglass energy. To avoid hourglass, you need to go for higher integration elements. So that is why QEPH24, it can always solve your issue right away with hourglass energy. Energy balance we have already studied. It is just trying to elaborate more and more about it. Same thing with mass balance. Now the added masses can have many implications. So if they are getting added on an element or node which is besides a spot weld, then you should also check the spot weld definition. So if the spot flag is 1, the mass is added at time equal to t0. So momentum balance is also worth looking at, though it may not be always be followed because of the continuously deleting elements from the analysis. But well, a good momentum balance tells a big deal about your current model. Then you will go for the visual inspection of the simulation through H3D file, and that can tell you if there is any non-physical behavior. So that animation will tell you first of all if there is any type 11 contact required in this case. If not required, then you should be good. If required, then you should definitely review that. So there are few typical debugging scenarios. Energy error, the solutions are listed over here. That imposed time step could be too high. That means your energy there is coming because of the high demand of the deforming parts. Now if the time step is too high, those deformed parts are getting skipped while simulation, and that is creating an instability and so the energy error. If the material is badly defined, then well, it results in non-physical stretch or non-physical cracks within the components, and that creates a problem. Same thing with mass error. If you have mass error, then you should look at your time step as well as material properties around that region with maximum mass error. So mass error, you can look at the mass error or the added mass using the H3D files. The negative volume is very common issue among people who are trying to make solid mesh. So as long as you are following the best recommended practices or recommendations for solid element card, you should be good. But in case you still feel that negative volume is issue, then you can take care of those things in the first place itself. The negative time step, that can be mainly because of the spot flag in your contacts. If you set it to 1 in interface type 2, then it should not have much issue. So with this, I'll conclude today's session. You have the 3 projects in front of you. You should start working on right away, and we'll see you next time in our live class. Meanwhile, whatever questions you have regarding these projects, you can post it on the group, and then I'll answer them as soon as possible. So for me right now, I'll try to put the picture for the points ABC, which will help you translate this impactor into proper location. All right, so thank you everyone for joining, and we'll see you soon. Thanks a lot. Bye.